This is where I live. This is our house. Solar panels on the roof, Tesla battery on the wall, feeding into the grid. And over behind you here, this is old stable block for when there were a lot of horses here. So we converted the stable block into the workshop, and the workshop is on the left over there. So that's where we do all our RepRap stuff. This, incidentally, is an ancient machine. It's not the latest generation. And it has a little bit of a backstory in that the first machines of this shape, this prism shape, were designed by my research student, a guy called Ed Sells, now Dr. Ed Sells, because he got his doctorate from doing this work. And then Joseph Prusa took that design and improved it very greatly. And then this machine here is me taking that design that he did and well, not necessarily improving it again, but adapting it to what we particularly wanted. So it's a very old machine, which still just about works. But the reason we got it out is because it's historically interesting, not because we necessarily use it for any serious printing. But it's got the electronics on the side here that we developed in conjunction with an American guy called Joe Mosfet. And when we're talking about RepRap electronics, that goes back quite a long way. So, for example, on the wall over here, this is one of the very first pieces of stepper driver electronics that we developed for RepRap. I'm guessing this would have been about 2006 or thereabouts. This is a homemade printed circuit, as you can see, and in fact it's two-sided. Another piece of history. So yeah, 2005. I had the idea in 2004. Back at the start of the project, my university had bought a couple of 3D printers funded by the government. In fact, I specified them. Now I knew about 3D printing. I had known about it for years, but I'd never used one of the machines before. And when we got them, it was a bit of a revelation, because it was suddenly like having, I guess it was a bit like what writers must have felt when word processors first came in and they had to move from a typewriter to something where they could just edit on the fly. This is what this felt like for engineering. You could literally just edit something and have it in your hand, you know. And for years before that, I mean right back to childhood, I've been interested in the idea of machines copying themselves. So I thought, finally, we got technology here in 3D printing that allows a machine to print most of its own parts. Not all of them, obviously, but most. So that was the genesis of the project. I originally thought about it in 2004, wrote the idea up as a document, put it on my university's website at Bath University, and I didn't originally think I was going to do it. I just thought, well, I'll put this idea out there. If someone's interested, they can take it up and they can run with it. But what happened was that many of my colleagues came and said, well, Adrian, why don't you do it? And so I thought, well, why don't I do it? And I applied for, in fact, I applied for the smallest research grant that I've ever applied for and was awarded it. And the reason I applied for such a small grant to start the RepRap project was I wanted to prove that the whole project could be done for less than the cost of a single 3D printer at the time. At the time, 3D printers cost about $40,000 or $50,000, and I applied for a grant for £30,000, £27,000 to be precise. It's slight cheating, because in addition to that grant, I also had a very good research student who was funded anyway because he was a very good student, and he worked on the project, so we also had input from him, which was obviously worth more money than the money we got for the equipment and so on. Anyway, so that's how the project started. I originally thought that I'd make it open source, because it seemed that the idea of a self-replicating machine was quite a powerful one, and that one had a certain duty to stop it falling into the wrong hands, and so the only way to stop it falling into the wrong hands is to give it to every hand. That's the reason why I originally open sourced it. But as soon as I'd had that idea, I mean literally minutes later, I thought, well, if you've got a machine that copies itself, you've got to open source it, because basically if you try and patent it or constrain it in some copyrighted way or whatever, what you're saying to the world is, here is my machine that copies itself, you're not allowed to copy it, which is crazy. And so that's two reasons why I decided to open source it. And that's basically how the project started. My university's publicity department put out a press release about the project, which I helped to write. And as a result of that press release, lots of people got in touch with me and said, oh, we'd like to help you with this as volunteers. So I had a stream of volunteers coming in from all over the world. The first one was actually Vic Oliver from New Zealand, who was right in very near the very start of the project, and he did a lot of work on the project. And other people, as I say, from all over Europe, the United States, New Zealand, South Africa, and so on. So we suddenly had a very large research team, with the great advantage that I didn't have to pay any of them any money. And that meant that the project really did get underway, because we could have quite a lot of work done, a surprisingly large amount, in fact, in quite a short time. My expectations of the project were really basically founded on I had no idea if it was going to work or not. I didn't know if it would work technically, and even if it worked technically, I didn't know if it would take off or not. So I did what anyone would do when they don't know the answer to something. I just awarded the possibility that it would succeed at 50%, 50-50, might fail, might pass. I knew that if it succeeded, it was probably going to succeed quite well, because anything that copies itself is capable of growing in number exponentially. And so if it didn't die out, either from lack of interest or because technically it wouldn't work, if it didn't die out, I knew that it would actually then go on to not exactly take over the world, but certainly spread pretty far. The current state of RepRap is that, in a way, I consider the project finished, in the sense that it's gone out into the world. There are hundreds of designs out there. People build the machines. Lots of the commercial 3D printers that are sold are based on the work that we did. So I personally am not doing any more research on self-replicating 3D printing. But other people are building new designs for machines, and as I say, it's formed the foundation of one large branch of the global 3D printing industry. So that's really where it is today, I guess. But as a project, it's sort of finished. I mean, projects are never finished in some sense, because people are always developing them and developing. Shown the idea works, it's gone out into the world, lots of people have built them, so that bit of the project at least is done. As far as the state of open source and 3D printing is concerned, I think that it's a little bit different to the way that open source works with pure software. If you look at pure software, there are open source companies like, for example, Ubuntu, commercially successful. Their product is entirely open source, and everybody sort of knows how that works. The difference with 3D printers is that, of course, you've got a piece of open source hardware, and you need a physical object, and that changes the dynamic rather slightly in how the whole thing works. Even with a self-replicating 3D printer like a RepRap machine, though that is rather more close to software than a non-self-replicating printer. But what's going to happen, I suspect, is what's been happening already, but more of it, namely some companies will try to patent things which have previously been open sourced, and of course such patents are completely invalid because the previous open source effectively establishes a prior art. But that doesn't stop the patents being awarded, because basically it seems that the world's patent authorities tend to take the view that they'll award the patent and then let the courts fight it out. But what tends to happen, I think, with 3D printing patents, when something open sourced is patented, is that the company patents it, the people who own the open source object, but it never quite gets to court because neither party can really afford the legal expense of pursuing it. So it remains a sort of open question. But equally, the companies can't really pursue people who are copying their patent. Of course, they're not copying the actual patent. What they're doing is they're copying the thing that was previously open source. And I suspect that things are going to go on pretty much like that. People in the community, private individuals, small companies and so on, are going to continue to develop open source ideas. And some people will genuinely have new ideas that they then genuinely choose to patent, and that's completely legitimate. But there'll be this continual tension as the whole thing goes forward that'll never completely get resolved, because it's continually being renewed from underneath by developments being made both by companies and by individuals. So I'm not sure that things are going to change very much. You'll have some open source companies, you'll have some companies that have closed source designs. Some of those closed source designs will be based on open source material, but the people in the open source movement don't really have the resources to pursue that. And I mean, they can condemn the companies, and of course social pressure is a considerable pressure. In some ways, it's a greater pressure than legal pressure in many circumstances. So it's quite possible for the community to shame a particularly badly behaving company if they try to close off something that was open source. And sometimes that can be effective, particularly if people stand up and make a great deal of noise on social media about the problems. As to what will happen, I don't know, but my suspicion is things will continue to muddle on in a confused mess, pretty much as they are now. Well, I mean, somewhere where the 3D printers are a little bit in an area which is in space. As you may know, they've flown a 3D printer on the ISS and use it to print things in zero gravity. But in 2 years' time, we'll be going back to the moon, and people have been looking at developing 3D printing systems that work with lunar regolith, which incidentally is one of the things that brought one of the very earliest RepRap pioneers, whom I've already mentioned, Vic Oliver, into the project. That was an aspect of the technology that he was interested in, using it for printing on both in space and also on other bodies in the solar system. Yeah, I mean, one of the great things about working on the moon is that you've got a vacuum and you've got not an infinite supply of energy, but an enormous supply of energy in the form of sunlight. Admittedly only for half the time, but that should be enough. And so the idea, for example, of 3D printing buildings, which we've already mentioned, perhaps it will be in lunar and then later Martian exploration that comes to its fore, rather than on Earth. Who knows? But that is an area which is not currently using a great deal of 3D printing, simply because of the cost of doing it and the fact that we've got conventional systems for getting things into orbit. But as I speak, the launch of SpaceX's Starship, the very first one, has just failed. It was a test flight, so that's not surprising. Test flights often fail. I'm sure they learned a lot from it. But once that system is working, the cost of getting things to orbit should be reduced really quite significantly. I believe Musk is talking about $200 per kilogram to orbit. Now, whether they actually get down to that number, I don't know, but we all own items that weigh a kilogram that cost $200. So we're starting to talk about sums of money to get things into space that are within the range of literally of private individuals. And I don't mean Elon Musk there, I mean just ordinary people. We can move 3D printing into space exploration, I suspect, without too much trouble in the next few years, whereupon it will become a very valuable way of making the stuff we want in situ, as opposed to having to carry it all there. Yeah, I can remember when I first met Joe. We used to run these workshops where people would come and build RepRap machines. So what we do is we get all the bits together, the printed parts and the stepper motors and so on, and we'd put them in a cardboard box as a kit for people. And then we'd have maybe a dozen people or 20 people in a workshop, and they'd all come and over a weekend they'd assemble their own machine. And Joe and a number of other people on the RepRap project came to one of those sessions that we were at, and that was the first time that I met him. He wasn't actually building a machine in the session. He was helping as he was there as an instructor, as it were, as was I, to help these people who were new to the whole idea to build their RepRap kits. And so that was the first time that I met him. And I can't quite remember if that was before or after he had designed his first machine, or whether he was in the process of doing it at the time. But it would have been around 2011, 2012, I guess. I can't remember the date exactly, but it would have been about then. I don't know the future, so it's very difficult for me to say where 3D printing will go in 10 or 15 years. Psychologists do experiments on people making predictions, and they discover that even experts are useless at making predictions. You might as well just ask someone on the street. There's one exception. They discover that people who actually make predictions for a living and get constant feedback, people like weather forecasters, are good at making predictions. But so-called experts like me know nothing about the future, so you can completely ignore what I'm about to say. Ever since the start of the RepRap project, I've been amazed that the world, everybody developing these things, both commercially and as hobbies and as private individuals and so on, haven't really been working hard towards putting good electrical conductors in 3D prints. Now, of course, you can get 3D printing machines and you can get conducting filament and you can print sort of electrical circuitry. But I'm surprised that that isn't considered to be the single primary activity that we need to work towards, because it seems to me that suddenly everything becomes much more versatile when you can make a mechanical object which has got three-dimensional electronics, and I don't mean printing the electronics, three-dimensional circuitry with conventional electronics embedded in it, embedded in a mechanical object. It may be simply because it's so cheap and easy to make printed circuits these days. You literally sit down with a CAD system, design a printed circuit, and I know you've taken this in-house at Prusa, haven't you? But you can get it made almost by return of post, not quite, but maybe it's a bit like the way that the motor car developed. When motor cars were developed in the 19th century, towards the end of the 19th century, they were all electric. Then the Model T Ford came in, and suddenly petrol took over from electricity, even though arguably electricity was the better way to do things. So we were stuck with 100 years of petrol cars. Maybe it's like that with electronics. It's so easy, just as the Model T was so easy to get going as a petrol car, it's so easy to make a conventional printed circuit that people aren't too fussed about putting electrical conductors into 3D prints. But it would make a lot of things possible that aren't currently done. Maybe that will happen, maybe it won't, but I don't know, because I don't know the future, as the psychologists tell us that I don't. Well, we have this little company. By we, I mean my family, and what we do is we do research on applications of 3D printing and also some consultancy work for people. So somebody might come to us with a 3D printing problem, which we'll try to solve for them, or we often do things off our own bat, like developing little robots and other things, just for our own interest and amusement, really. Though we open source everything that we do personally, so the designs for everything we do are online. This is a little robot. It's a commercial robot. It's called Petoy, but we've been extensively modifying it. It's a simple little walking machine in its original form, but what we've done is we've added some extra electronics to it. It has the option to have a Raspberry Pi attached to it, which gives it far more processing power. But in addition to adding the Raspberry Pi, we've also added a camera on the front and a LiDAR rangefinder, so that it can take images and find out the distance to what's in front of it. And we've also modified the lower legs of the robot so that when it puts a foot down, the foot moves very slightly, which it can sense, so it knows when it puts its foot on an object, and that allows it to walk over rough ground because it can adapt its stride so that when its foot touches something, it stops carrying on moving downwards. And finally, It's got electrical contacts on the feet, these little gold threads that you may be able to see running around there. And the robot, when it's finished, will automatically find its charging mat, which is this thing here. That'll be on the floor, and when it walks onto that, it can recharge itself from those 4 copper plates. And it'll recharge itself whatever orientation it's in on there, because of the way that the electronics works. So that it can be completely autonomous, and when it's finished we'll have it wandering around the workshop pretty much permanently, being tripped over by people and broken. That's a project that we're doing mainly for interest, but when it's finished we'll open source it. Well, it is already open source, you can get what we've done so far on GitHub, but we'll open source it and perhaps offer it to schools so that children can both 3D print the robot and also experiment with the electronics and the software that goes with it. We've already got the workings of an AI system for the vision, the camera that it's got, so that it can find its way around purely by sight. The way we did that, there's a fairly straightforward programmable neural network available online, which will work with images. And what we did was we just simply moved around the floor in here with a camera at the same height that the robot is, taking a whole series of random images, and obviously what it needs to know how to do is to walk to the charging plate. So for each of those images we categorize them as go straight, turn left, turn right, or search. Search means turn round and round until you find something you recognize. And with those categorizations of all the pictures taken of from the robot's point of view, the robot should be able to find its way to its charging plate wherever it finds itself in the room. This is a paint mixer. What we're looking to do is to make a painting robot. Ultimately it will use the Cartesian frame slung from the ceiling that I showed you before, but at the moment this is just the mixing system for it. So what we've got here is the 3 primary colours, cyan, magenta and yellow, together with black and white, and those syringes filled with those colours fit in these 5 stepper motor syringe drivers here, and so you can mix the primaries and black and white in any proportions that you like, and so you can get any colour that you like out of it. This was our first test paint, as it were. This one was actually done without the black, so the colours here are not sufficiently dark, and we decided after we'd done this experiment to add the black. Initially we're just going to use it as a painting mixing system so that we can paint by hand, but have the system automatically mix the right colours for us, as opposed to us having to mix the right colour ourselves. But ultimately what we'll do is we'll have the robot both mixing the colours and also painting the painting based on, who knows, an image from Midjourney, whatever it might be. And in fact, if you look above his head over there, you see there's a rather weird Mona Lisa on the wall, very high up. Years ago, my students, when I was at the university, had a robot paint that version of the Mona Lisa from the original Mona Lisa, though they modified the smile, as you can see. They thought they'd make the smile a bit more emphasized, and so that's quite an old experiment now. That was done 25 years ago or something. So having a robot paint a picture is not a new idea, but I hope this one is going to work rather better, and in particular will have rather more colors than that one displays. So this is our mechanical workshop, largely conventional manufacturing machines in here. This is my ancient lathe, which I've had for decades. As you can see, it could do with being cleaned, but it works very nicely. Ordinary pillar drill, computer there that drives a little CNC milling machine, 3-axis milling machine. This is where we do basically conventional mechanical engineering when we need to make something out of pieces of steel or whatever. So nothing very revolutionary in here. This is normally sort of vaguely a chemistry laboratory in the workshop. We do actually have a license from the police to work with explosives because one of the things we're looking at is developing a new type of solid fuel rocket engine. The idea behind it being that in a conventional solid fuel rocket, of course, you have a tube filled with what is essentially explosive, and that explosive burns. But it occurred to us that the material that you put in that tube could be formed into a filament, like the filament for a 3D printer, and then fed into the engine, rather as you feed 3D printer filament into the hot end of a 3D printer and burned in the engine. So you've got a combination of solid fuel, which is very stable, can be kept forever, and the advantage of a liquid fuel rocket, which is that you can turn it on and off. In particular, you can turn it off and then turn it back on again, which you normally, once you start a conventional solid fuel rocket, it's got to burn to the end. So anyway, that's something we're developing, and again, open source, of course. And so we've actually got an explosive license to allow us to make the fuel for the rocket, which was quite interesting because the police came and looked around here and said, "What's that? What's that?" And we had to explain everything that we had. This is our storage room, which is even more chaotic than normal because we're renewing some of the floors out there, and so all the stuff that was in the rooms where we're changing the floors has been moved in here to get it out of the way. We've got various old machines. We've got a lawn mowing robot up here, which is broken, but which I'm going to repair at some point. This is my piano. The piano lives out here. It could live in the house. The rule is that if the piano's in the house, I have to use it on headphones. But if it's out here, I can play it live with open sound. So the piano actually lives out here. Oh, here's an interesting thing, perhaps. That's a Delta printer that I was developing, indeed sort of still am occasionally from time to time. It's got a few interesting things about it. First of all, as you can probably see, there are no wires going to the top of the machine. There's a wire at the top of the machine going down to the print head, but all the electricity going to the top is actually conducted through the vertical bars, the sliders. So you've got six electrical connections going from the bottom to the top, just using the metal of the sliders, because it's all low voltage. That's fine, of course. We've got an additional thing here. They're hollow, so you can actually run wires up the inside as well, and the wiring in the bottom of the machine, and indeed at the top, actually runs through the printed sections. So the printed sections have all got holes in, and you just poke wires through to make them all neat. And the other thing about this sort of machine is that you have to adjust the lengths of all the components very precisely. So if you look here, you can see that these two sections here are actually joined together in the middle. But what you do is the critical thing about these two is the distance between these two vertical rods here. So what you do is you measure that distance very carefully, and then you just put a screwdriver in this gap and very gradually adjust it until it's just right. And then you just pour super glue down these two holes here, sets the whole thing rigid, and it's spot on, frozen forever, and never goes out of adjustment. The vertical movement is with wires wrapped around cylinders as opposed to a tooth belt, which seems to work quite well. Anyway, that's a thing that I've been playing around with for a few years. I'll put it back. Still just about accessible behind the telescope is a Prusa printer that was very kindly given to us by you guys, and we use that quite a lot when we want the most precise prints. It's extremely useful and works, I'm pleased to say, very nicely. Do I have a message for the 3D printing community? I personally would love it if everything stayed open source, but I realise my influence over things is very limited. So if other people can work towards that, then that would please me greatly. But the amount that I can actually cause to happen is, of course, slim indeed.